All right, welcome you guys. So we're going to talk about exponential functions today. And in the end, we'll use E, which we're going to learn about today, the number E, to help us do some applications problems involving interest. All right, here we go. So we have this definition of an exponential function here, and it's very specific how it's defined. Okay, so it says the function f of x equals a to the x, where x is a real number and a is greater than 0 and not equal to 1. That's called an exponential function with base a. So I've given here some examples of what's not exponential. A lot of students will think these are exponential. Even in my calculus class, they'll kind of confuse exponentials and polynomials, okay? A polynomial has a number in the exponent, so that's not what we're going to call exponential. For it to be exponential, it has to have the variable in the exponent. And you can sense that that's new. We're used to having x down on the base, but now we're having x up in the exponent. And there's a little bit more to it. You notice if you look at the directions, it says a cannot equal 1. So one of the reasons a cannot equal 1 is just because it's boring. Imagine if you did have y equals 1 to the x power, right? Well, it doesn't really matter what you would substitute in, right? If you had 1 to the 0 power, anything to the 0 power is 1. If you have 1 to the first, it's 1. If you have 1 to the second, well, that's 1 times 1, which is 1. If you have 1 to the third, that's 1 times 1 times 1, that's still 1. Like, all we're going to do is get this extremely boring and uninteresting graph of a flat line through y equals 1. And so this doesn't fit the bill for what we want when we're talking about exponential growth or exponential decay. This isn't even worth investigating. It's kind of boring. Okay, so now it says right here that a has to be greater than 0. So that base has to be a number greater than 0. Well, let's talk about what would happen if it didn't and why we make that restriction. So let's say we have negative 2 to the x power. Now, this is very problematic because if I were to take like fractions, let's say any sort of fraction, I don't know, 1/6, whatever. What that would mean is that would mean negative 2 to the 1/2 power, or in this case, negative 2 to the 1/6 power. Well, let's go investigate what happens, and we'll talk about why this happens, okay? So if I put in, I make sure I use parentheses because I want that negative to also get the exponent. And I raise it to the 1/2 power. Well, you can see we get a math error, okay? And it turns out that you're going to get an error for any non-integer value. So anything that's not a whole number, okay? So we can't even substitute in things that aren't integers, okay? So the domain wouldn't allow non-integer values. That's how we say that. Remember, integers are positive and negative whole numbers. So decimals like 0.23, fractions like a fifth, all of these things, etc., would not be allowed. And that's no good. We know that we want these functions to be continuous. When I plug in a value, I should get a value out for the most part, right? In fact, on our exponentials, we will for every value, okay? So our typical exponential graphs look like this. We'll talk more about these in the future, but you can substitute in any value you want and you will get a value out. So that's why we don't allow negatives. They aren't defined for values like a half. And so you would just be getting some really funky graphs. You would be getting graphs where like you only have a value at like 1. You only have a value, let's see here. I should have probably made that negative. You only have a value at 1. You only have a value at 2, etc., at 3. And then in between, there wouldn't be anything. So you'd have this discontinuous, this discrete data if we allow for a negative base, which is no good. Okay, so let's just kind of recap. It's called exponential because x is in the exponent. That's the biggest piece of it. So we have to make sure that the x is in the exponent. And we have to exclude bases like 1 and bases that are negative, because 1 is boring and negatives are highly problematic because we do not get values out when we plug in a lot of numbers. Okay. All right, moving along. So we are going to have the two cases that I drew a second ago. All of our exponentials are going to come out either looking like option A or looking like option B, and we'll talk more about this in a second. Of course, we could reflect these, we could translate these, etc., right? We could dilate these or have stretch or shrink to them. But these are basically what all the parent functions are going to look like. Okay, so let's go in here and try. We'll start off with t-charting. That's how we start off with every graph. All right, so we're going to go ahead and do 3 to the negative 2, 3 to the negative 1, 3 to the 0, 3 to the first, 3 to the second, and 3 to the third. All right, now a negative exponent means you've got to move it, and you got to put it in the bottom and make it a positive exponent. Or in other words, put it under 1, right? So this is actually going to become 1/9. I find it's quicker to just know that than to substitute it into my calculator. All right, so this is going to be 1/3 to the positive first power. So in other words, 1/3. Anything to the 0 power is 1. And now we start getting into the easier ones. 3 times 3 is 9. 3 times 3 times 3. So 9 times 3 is 27. So, all right, we're going to graph these points. And it's me kind of sketching it because, you know, these 1/9, no one's going to know really if I'm at 1/9. Now keep in mind the y-axis here is counting by 3. So like 1 might be right here, 2 might be right here. I just want to make sure we keep that in mind. So when I go to -2 for the x and 1/9 for the y, it's going to be so small that you really can't even tell. All right, -1 1/3, small, but a little bit bigger, a little bit higher, I guess I should say, a little higher. And then 0, 1, 1, 3, 2, 9, and 3, 27. Okay. Now this one, you've got to understand that there will be an asymptote, a horizontal asymptote for all of these exponentials. And in this case, where there's nothing attached to the back end of this 3 to the x, then your horizontal asymptote is always going to be 0 for the ones where there's nothing attached to the back end, okay? So that's why I made my horizontal asymptote here at, I'll just put HA for horizontal asymptote, at y equals 0, okay? All right, so we are not going to touch that asymptote. We'll get really close to it, but we're never going to cross it. And there is our graph, okay? Now you can cross horizontal asymptotes. We already talked about that when we were graphing rational functions, but not with these exponentials. It turns out the exponentials never touch. And I mean, you could just kind of think about that. This is 3 to the x. And we want to know, is it ever going to be 0, right? Is it ever going to touch that red line, which is 0? There's no exponent that we could plug in that would make that happen. Like we already said, 3 to the 0 is 1. We already said when we substitute negatives in, it just brings it down to the bottom. So there's just no way for us to get 0 out. And that's the reason why this will never touch 0. You get really, really close to it, but it won't ever touch it in this case, okay? So I'm just going to put a little comment that exponential graphs never touch their horizontal asymptotes or never cross. Oh my gosh, horizontal asymptote. Okay. All right, so there is our graph of 3 to the x. Now, we would label this as exponential growth. And I think it's kind of obvious why. As time increases, we're going to consider the x-axis time. As time increases, the graph gets higher and higher and higher and higher and higher, and it gets higher fast. That's one of the qualities of exponential growth. You might have heard somebody talking before and saying something like it grew exponentially. But what they mean when they say it grew exponentially is they mean it grew fast. Because if you think about a line, like let's consider y equals x, it's getting higher and higher, but it's getting higher and higher at a really slow rate. I mean, we plugged in 1, we got 3, we plugged in 2, we got 9, we plugged in 3 and we're already at 27. Just to let you know, the next one would already be at 81. So the growth, when someone says something grows exponentially, they're saying it grows really fast. All right, let's try this next one. All right, so now we have 1/2 as our base. That's definitely exponential. The x is in the exponent, and we have a number that is not 1 and is not negative as our base. So we're going to have to figure out what 1/2 to the -3 is, which, believe it or not, these look scary, but these are the best ones, the ones raised to a negative power. You'll see why. The ones that are raised to positive, to whole number values, are the ones that are actually the ugliest in this case. Okay. So whenever you have a negative exponent, you just flip it. So like instead of 1/2, it's 2/1, and then you change the sign on the exponent. So this is essentially 2/1 is just 2, right? So this is essentially 2 to the third. Well, 2 times 2 times 2. 2 times 2 is 4, times 2, 8 is going to be the answer. And that's a nice answer. So something that starts off this ugly actually came out to be pretty darn nice. Let's try it again. So we know that if a fraction's raised to a negative, we flip it and we make it a positive. And so this is really just 2, because 2 divided by 1 is 2 squared. So we get a 4. Sorry, my 2's are kind of ugly. Flip it, make it to the positive first. 2/1 is just 2, and 2 to the first is 2. Anything to the 0 power is 1. Anything to the first power is itself. And 1/2 multiplied by another 1/2. If we multiply 1 times 1, we get 1. 2 times 2, we get 4. So actually the whole number exponents gave us kind of worse values. All right, -3/8. Again, we're counting by 2's on the y-axis, so just be careful. -2, 4. -1, 2. 0, 1. It's going to be 1 right there, you guys. 1.5. So half of that is going to be right there. And 2 and a 4. So half of that. So again, there's still that horizontal asymptote of y equals 0, because we don't have any number being added or subtracted to the back end of this exponential. So most of the time in this class, it will be y equals 0. Okay, so we're going to go ahead and graph this one. Now this one cannot be called exponential growth, because as time goes on, as time gets positive, bigger and bigger, we're actually shrinking. So this one is called exponential decay. So all of our graphs will look like these last two, provided we haven't reflected it or we haven't translated it. Okay. All right. So let's just kind of talk about these two graphs. So I want you guys to quickly look at the function and be able to tell me whether it's going to be growth or decay. So let's talk about that. I remember being in the classroom one time and I had these cheap calculators I bought from the 99-cent store for my students. And so a lot of times the buttons didn't work. Okay. So a student calls me over and they were like, hey, Mecklenburg, my calculator's broken. Can I get another one? And I was like, oh, okay, why is your calculator broken? And they had something like 0.67 and they were squaring it, right? So let's go square 0.67. So 0.67 to the, oh, I'm not, sorry. There we go. Let's try this again. 0.67 squared. Let's turn that into a decimal. Okay. So I can see why the student said, hey, my calculator's broken. I asked them, well, why do you think it's broken? And they said, because I squared it and the number got smaller. So if you take 0.67, you square it, you get 0.44 or 0.45, right? So it just shrunk. And this weirded them out. Okay. But not all numbers, when you square them, get bigger. And that's essentially the heart of what we're talking about here when we're saying exponential growth versus exponential decay, okay? When you raise a number, let's say 2, for example, to higher and higher exponents, yes, it grows. Okay, 2 to the 4th is 16, okay? But that's not always the case. Consider something like 1/2, what we just did, right? But when we squared 1/2, if you recall, we got 1/4. That actually got smaller. And I mean, it gets worse if you do it to the 3rd power. Because now I have to do 1/2, 1/2, 1/2, right? 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. Wow, this got even smaller. And the next one's going to be 1/16. You probably see the trend if you look over here. These are the denominators, right? Okay, so what we really want to narrow down is, now that we understand squaring doesn't mean it's always going to grow, what we really want to narrow down is, okay, well, can we find out what types of numbers are going to grow and what types of numbers are going to decay or going to shrink? Now, usually when I ask this in class, I'll have a student say, well, fractions, if you square a fraction, then it's going to get smaller. I totally see why they would say that from these 2 examples I have up here. But let's go and investigate that. What if I have 3 halves and I say, okay, let's take 3 halves and square it. By the way, 3 halves is 1.5, you guys. So 1.5. So if I square that, I have to do 3 over 2 times 3 over 2. Well, 3 times 3 is 9. 2 times 2 is 4. And by the way, that's 2.25. Okay. So I just gave an example of a fraction that actually grew when I squared it. So I want you to kind of think, maybe guess before I tell you what kinds of numbers, what kinds of fractions in particular, are going to shrink and what kinds of fractions are going to grow. Okay, so let's put this together. So here's when we're going to have growth. Versus when we're going to have decay. Should probably put exponential in front of that there. Okay. And this is all going to be for functions of the form a to the x power, right? This is for a to the x. If the base a, so if a is greater than 1, then we're going to have growth. I'm just going to put then growth. I know that's bad language, but let's just get to the heart of it. Notice 2 grew, and so did 3 halves. It grew, and notice it was bigger than 1. Okay. For the exponential decay, if the a is a proper fraction, so not an improper fraction, and so what we would say is an a that's bigger than 0, because remember, a can't be negative. That was the definition of exponential, but less than 1. Proper fractions are fractions where the top is smaller than the bottom. Those are always going to decay. And these are always less than 1. Remember, 5 over 5 would be 1. So 4 over 5 would have to be less than 1, right? Okay. So any fraction that's proper, aka in between 0 and 1, that's going to decay. And I know a lot of you guys love decimals, but honestly, go fractions in here, because think about it. If you have 2/5 and I say to square 2/5, well, 2 times 2 is 4, 5 times 5 is 25, done. But if you turn 2/5 into 0.4 and you have to square it, that was not too bad. But it's still a little bit tougher if you're not really good, you know what I mean, with decimals. In fact, I bet a lot of people might even get it wrong, okay? So yeah, I wouldn't go decimals in this section. I would try to keep things as fractions. It's going to be a lot easier to do the math. All right, so to recap, if a is bigger than 1, then we expect exponential growth. If a is between 0 and 1, then we expect exponential decay. All right, you guys. All right, now this is going to bring back all those transformations that we learned earlier in the semester, okay? And it's kind of a little recap down here in the bottom corner, okay? So if we have some sort of exponential, the number out front does the shrinking and the stretching. The number inside here, that's going to shift it left or right and it lies. The number on the back end is going to shift it up and down and it tells the truth. So just kind of reminding you guys. Also, if this A is negative, it's going to reflect over the x-axis. Okay. All right. So what the homework is probably going to have you do is it's probably not going to have you just go straight in and t-chart this guy as is. It's going to say, okay, well, what's the parent function? So remember, the parent function is when you take away all the transformations. So you take away, by the way, let me rewrite this in what I think is a better form. So that's me kind of trying to write it like what you see down here in the bottom corner, okay? All right. So if we take away the negative sign, we're taking away the reflection. We take away this +1, we're getting rid of the horizontal movement. And if we get rid of this +1, we're getting rid of the vertical movement. Now we've got a transformationless parent function, okay? Now, they want you to t-chart that because that's just going to be super easy to t-chart in comparison to this thing, right? So that's why we're doing that. So we're going to go 2 to the -2, 2 to the -1, 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. Now remember, anything with a negative exponent, move it down to the bottom, make it a positive exponent. So this one's going to be 1/4. So -2 up 1/4. So maybe right there. Anything with a negative exponent goes down to the bottom with a positive exponent. So we got 1/2. So -1 and then 1/2. Anything to the 0 is 1. 2 to the first, just itself. So 1, 2. 2 to the second is 4. So 2, 4. And 2 to the third is 8. So 3, 8. Now this is not the final answer. So I am going to make this dashed. I'm going to label it so we know what's going on. This is just 2 to the x. All right, now we're going to take care of all of the transformations. And we said, think of the alphabet RST. We've got to reflect first, order matters. Then we're going to do the stretch/shrink. We have one. And then we're going to do the translate. Okay. So let's start off by reflecting. So we're going to reflect because of, let's just kind of analyze this guy. We'll put him over here where we can write about him. The negative out front is what's going to make it reflect over the x. So let's start there with the R, the reflect. Okay, so I'm going to try to reflect all of these points over the x-axis. 1, 1, 2 away, 2 away, 4 away, 4 away, 8 away, 8 away. Okay, so something like this. I'm still going to make it dashed because this is not the final answer. This is only -2 to the x. Okay, so we reflected over the x-axis. Now I always do the transformations in one shot because I feel like that's not too bad. That's kind of easy to do. So this -1 right here lies to us. So instead of going to the right, we're going to go to the left 1. And then this +1 tells the truth. So we are going to go up 1. So we need to go left 1, up 1, left 1, up 1 with all of our points, okay? So with this one right here, if I go left 1, up 1, I'm here. Left 1, up 1, I'm here. Left 1, up 1, I'm here. That same dot I just covered, left 1, up 1, I'm here. Left 1, up 1 puts me here. And left 1, up 1 puts me here. Now, I told you guys earlier that the back number is going to be the horizontal asymptote for these exponential functions. So we have a horizontal asymptote at y = 1. Now that's helpful because that's going to guide you. It's going to guide how you're going to draw your graph. You know you're not going to pass y equals 1. So when I connect all these green dots, right? Okay. I know I'm not going to go past that red line. And notice I made this one solid because this is the final graph of f of x. Okay, so a little review of stuff that it feels like it's been a while since we've covered. Okay, all right. So let's just take what we just did and make sure that we remember all that old stuff. Like, would you be able to tell which way you're moving? Okay. All right, so let's take a look at A. We want to look at what this minus 4 is going to do to the exponential 3 to the x. So take a second to guess and see if you remember. Now, since this -4 is inside the function, it's not like tacked onto the back end, it's inside the function, this one lies. So instead of right 4, this is going to be left 4. A and B have a subtle difference. That -4 or -4 is just tacked onto the back end. It's not inside the function. So this one's telling the truth. This one's going to go down 4. So remember, if it's inside the function, it's always horizontal movement. If it's tacked onto the back end, it's up and down, it's vertical movement. I'm going to rewrite C. I don't like how it's written. It's not easy for me personally to see all the transformations. So I'm going to write it like this, just for consistency's sake. So we actually have a couple transformations here. We have a negative out front. So that is going to reflect over, hopefully you remember, the x-axis. You're probably going, hey, I don't remember when it does the y. If it had done the y, the negative would have been with the x, like that. It would have been inside the function. Okay, now +2 we got to deal with. So this is not inside the function. It's just tacked onto the back end like b, like the -4 on b. So this is going to control the up and down, and it tells the truth. So we are going to go up 2. Okay, so hopefully that kind of helps you review a little bit what we learned quite a while ago. Okay, we are going to add another irrational number to your tool belt. So you've all heard of pi, and you remember that pi was an irrational number because it was a decimal that goes on forever, 3.14159, blah, blah, blah. It never stops. So that's what an irrational number is it's a decimal that's non-repeating and non-terminating. Okay, so it's just going to go forever. Well, we're adding now another irrational number like pi, e. So when you see e, it's not a variable, it's an actual number. It's like 2.7-ish. So it's pretty close to 3. So when we see e in here, always remember it's a number, it's about 2.7, but it actually goes on forever. Okay, and there's no repeating. This is our technical definition of E. I had to put this in here, I felt like, because we talk about it in calculus 2 a lot. So I wanted to make sure that this was something that people who are planning to continue on see. If Math 105 college algebra is where you stop, don't know that this is super important for you. But for those of you that continue on, as x goes to infinity, this expression approaches E. Okay. All right. So let's just get used to finding E on our calculator, using our calculators to get these values. We're not going to do it by hand. You saw how ugly E was. So let's go ahead and go in here and get E squared up to 4 decimal places. Okay. So E, where is it on this calculator? It's right here. So I have to hit the yellow shift button to get to it. All right, we want just E squared. Well, 3 squared is 9, so this has to be a little bit less than 9. Let's see. 7.389. Okay, so we're going to round in 4 decimal places. So 0 is the 4th decimal place. So 5 is behind it. So it's going to round it up to a 1. 7.3891. e to the negative 3. All right, shift e. Don't forget the negative is different than the minus on a lot of calculators. All right, 4 decimal digits. So 7 is in the 4th spot. 8 is going to round it up. So it's going to be 0.0498. 0.0498. E to the square root of 7. Four decimal places. So 0 is in the 4th. 3 is going to keep it as 0. It's not going to round it up. So 14.0940. 14.0940. All right. E to the pi. E to the pi. Okay, this is going to force me to find my e and my pi. Oh, try that again. Shift E and then shift. All right, 4 decimal digits. 6, but there's a 9 behind it, so it's going to become a 7. 23.1407. 23.1047. Okay, cool. All right, so that's just us getting used to our calculator. All right, now this one you could just graph e to the x, and then because there's a -1 inside the function, it's going to shift it right 1. But we're just going to t-chart it as is because it's not that complex of a function. So, it should be pretty simple to just substitute some values in. All right, so let's go ahead and pick some values. So maybe -2, -1, 0, 1, 2, 3. See what happens. So we are going to use our calculator. Substitute in -1. Now, if you're terrible with your positives and your negatives, then, don't do what I'm doing. But I think it's easier for me to combine these two. So this would really be e to the -3, e to the -2, e to the -1. 1 minus 1 is 0. 2 minus 1 is 1. And 3 minus 1 is 2. Okay. Some of these I know, like anything to the 0 power is 1. We just learned that e is 2.7-ish. So I'm going to put 2.7 with an approximately. All these are going to be approximately. And didn't we just square e on the last page and it was like 7 point something? 7.3, 7.4-ish. So we'll just go ahead and put that one in since we already did it. All right, now let's go to our calculator to get some of these other values. All right. So e to the -3. All right, so that's 0.05 is what I'm going to say. Boy, that's so small. I'm not even going to be able to graph that guy. All right, let's plug in. That's an approximately sign, you guys. I feel like compelled to put that so people don't think it's equals. All right, e to the -2. 0.14. That's really small too. E to the -1. 0.37. Oops. Okay. So I'll try my best to graph this. Now, before I start it, you guys should be able to tell me whether or not this is growth or decay. Remember we said if the base is greater than 1, it'll grow. If the base is a proper fraction between 0 and 1, it'll decay. Our base is e. E is greater than 1, it's 2.7. So we should have growth when we end up graphing this. Okay, so at -2, I'm at 0.05. That's like so incredibly small, I can't even show it. At -1, I'm at 0.14. It's small, but a little higher. At 0, I'm at 0.37. Maybe right here. It's a little higher than that. All right, 1, 1. 2, 2.7-ish. And 3, 7.4-ish. That certainly does show exponential growth, right? And there is no number being added to the back end, which means our horizontal asymptote is going to be y equals 0 again, okay? We could put a plus 0 on the back end, so we understand that it's going to be y equals 0. All right, so let's go in here and make sure we don't touch this particular horizontal asymptote. There we go. There's our graph. That looks great. All right. So let's use exponentials and just this one word problem here, because we're going to have a whole section where we do word problems with logarithms and exponential. So I'll just throw this in here. Okay. So we have 3 different types of interest. We have simple interest, which is honestly rarely used, but we have used it before in a couple of problems in our class. But now we're going to add in compound and continuously compounded interest. So simple interest does not give you interest on your interest. It's going to give you the same interest every year, depending on that original amount. So like simple interest, let's say you invest $100. Okay. So let's just go ahead and make, let's see here. We'll call this the year. And then we'll call this the amount. Okay. So let's say you're starting year 0, you deposit $100. And let's say that you get, I don't know, 2% interest. So you'll get $2 the first year. So now you have 102. You're still going to get $2. You're going to get $2 interest every year. So that's what simple interest would look like for the first 3 years. Okay. It's always going to be plus 2, plus 2, plus 2 every single time. You're not going to get interest on your interest. Okay. But if we go to compound, the difference between compound is that it does allow interest on the interest. And because of that, it grows a little bit faster. Okay. So let me go ahead and do the same scenario. You deposited 100. Okay, year 1, you will have 102. But now I'm not going to add 2. I'm going to add interest on this extra $2 I have now. So I'm going to figure out what 2% of 102 is. 0.02 times 102. So my interest isn't going to be $2. It's going to be $2.04. I'll take the extra 4 cents. Oops. So the first time we added 2. Plus 2. The next time we added $2.04. Okay, for year 3. Okay, I'm going to do interest on 104.04. So 0.02 times 104.04. So my interest is going to be $2.08. I'm going to add the $2.08 to my $104.04. Now I have $106.12. All right, so I mean, we didn't have a very big principal. We didn't have a very big original amount. So we're just getting barely more than we had over here, right? But imagine that your investment was much higher, or imagine that your interest rate was much higher. Well, then there would be a significant difference between using simple interest and compound interest. So hopefully that we understand the difference between simple versus compound interest. Now, the compound interest formula is actually pretty complex. I mean, look at that. Okay, the continuously compounded is not, but this compound interest one is pretty complex. So let's go in and make sure that we understand all of the pieces of that formula. All right. So the A is going to be, and I shouldn't use my writing. My writing's terrible. So let me just okay. So A is going to be the amount in the account after T years. It's all going to be in terms of years because they usually give you interest rates as an APR, an annual percentage rate. So we're going to let our time be years. Okay. Now P is referred to as the principal. That is just the original amount. The amount either invested or borrowed, whatever, but it's the original. R is going to be your rate as a decimal. It's always given as a percent. So make sure you convert it into a decimal. So move the decimal twice, right? To convert from a percent to a decimal. T is time in years. So this could be tricky if somebody's like, find it after 4 months. I'll have some students who will plug 4 in for the time. It's got to be in years. So if you have 4 months, that's not even 1 year. That's a third of a year. So you're always going to have to make sure you convert to time in years. Now, probably the most complicated part of this is N. N is going to stand for the number of compoundings per year. Oh my gosh, I can tell you. Compoundings per year. Okay. And it'll tell you that in the directions. It might not be blatant and say N equals 5. It might be like it was compounded quarterly or compounded daily or monthly or something like that. Okay. So you're going to have to figure out that N in each problem. Okay, so hopefully that helps you to understand what each one of those variables stands for. Now, the difference between this formula here and the formula on the bottom is simply the word continuously. They're both compound interests, but if you see the word continuously, you know you're going to use this bottom formula. And we actually get the bottom formula by letting the N, the number of compoundings per year, go to infinity. So in Calc 2, that's something that we show. We show that you can get this formula down here from this one by letting N go to infinity. Okay. All right. So kind of foreshadowing some stuff for those of you continuing on. All right, so suppose that $15,000 is invested with 2.5% interest under the following compounding options. Determine the amount in the account at the end of 7 years. So let's just go through and start, labeling things. That 15,000, suppose 15,000 is invested. That's going to be our original amount. That's going to be our principal. With a rate of 2.5%. Now remember, the rate can't be a percent. It has to be a decimal. So we're going to take that 2.5% and we said we're going to move the decimal twice. So it's going to go right here. So you have to put a 0 in. So it's going to be 0.025. Oh my. I hate when the board glitches. So I'm going to get all the glitches out here. All right, 0.025. 7 years. Cool. It's in years. We don't have to do any converting. We look good. Now, I don't see continuously compounded. I just see compounded annually. That tells me that I'm going to be using this formula. Now, we got to get the N, the number of compoundings per year. Well, it says it's compounded annually. That means 1 time per year. So we're going to put a 1. All right, let's substitute everything in and we'll just go to our calculator to have it do the math for us. So 0.025 over 1, 1 multiplied by 7. All right, and you'll see when I put this into the calculator, I'm going to put in, well, 0.025 divided by 1. That's just 0.025. And you add 1 to that, you get this. So I'll probably put this in to make my life easy. And 1 times 7, I might as well just put a 7. It's like, why type in all that terrible stuff when we can type in this much easier function? All right. So I'm going to do 15,000. Parentheses 1.025. This is exponential growth because it's bigger than 1. Should grow. Oops, what is that? Delete to the 7th. All right, so this is nice because this formula just goes right to the amount in the account. It doesn't give me the interest, it just gives me the amount in the end. All right, so $17,830, it's money. So we're going to take this 6 and round up to 29 cents. 17830.29. 17830.29. So you'll just have to know it's money, rounded the cents. All right, let's try this again. Nothing has changed, same scenario. But now we're going to compound quarterly. So instead of the n equaling 1, because we only did it annually, quarterly means we're going to do it 4 times per year. So n would be 4. So everything else stays the same on our formula. Okay, we're still going to be initially investing the $15,000. The rate is still 0.025. Okay. I'll just put this in as is for those of you who like to do that. I'm not clean it up. I probably put 28 in the exponent, but whatever. All right. So we're going to go ahead and put in, let's see, 15,000. 1 plus 0.025 fraction divided by 4. Right, parentheses. This is all going to be to the, I'm going to put 28. 4 times 7 is 28, you guys. All right, so this should be a little bit more, and it is. It's going to be 96 cents. So 17858.96. 17858. That's more. Let's see how much more. I forgot what the other one was. So 830. We have 858. So that's like $28 and some change more, right? And that's just because we changed the number of compoundings. So in other words, instead of doing it once per year, because we're doing it 4 times per year, we're adding that interest back into the pot to get interest on our interest. So that's why it's going to be a little bit higher every time. So now this one mentions the word continuously, and that's a big deal because that tells us, hey, change your formula to the PERT formula. Okay. All right. So PERT. So the principal is still the same. We still invested 15,000. And E is not a variable. We still have the same rate. And we still have the same time. So we just got to put this into our calculators. 15,000 to the 0.025. And this one's going to make us the most because this one was compounded continuously. 69 cents. Okay, so compounded continuously, we're adding that interest in all the time, right? It's like, okay, compute interest, put back in, compute interest, put back in. And so this one's going to be the biggest bang for our buck. Let's see here. That was $10 more than the one right before it, huh? 868, and the other one was 858. So we got 10 extra dollars just by making it compounds continuously. So playing around with these and seeing, how much extra money we're getting just depending upon how they decided to compound it. It's really good to understand because then if you go into a bank or you go into buy a car or something and you can find out your compounding, of course they'll tell you your APR, but you might have to ask, well, how is my compounded? How often is it compounded? You can find out how much extra money you're going to be paying if you borrowed or how much extra money you're going to be making if you invested. All right, you guys. So that is the beginnings. We're going to continue talking about exponential growth and decay all throughout chapter 5, but that's a great start. Thanks for joining me. Take care.